To build a parser, you must choose a direction. But when logic flows only one way, it can trap itself in an inescapable cycle. Up to this point, we've relied on top-down parsing. The logic is straightforward. You start at the root, the highest level grammar concept, and try to generate branches downward until they match the raw input string. But this downward flow introduces a serious flaw. If a rule references itself, like defining E as E plus T, the parser blindly generates E's forever. It is caught in an infinite loop before seeing raw data. Because it constantly tries to generate the structure before seeing the input, the system is fragile. It breaks against the very grammar rules it was designed to evaluate. To fix this, we must invert the entire architecture. Instead of starting at the root and working downward, we begin directly at the input leaves. Top-down generation is driven by leftmost derivation. Our inverted engine uses the mathematical opposite, rightmost derivation in reverse. We take raw data and condense it backward through the grammar until it reaches the core start symbol. By reversing the flow, the parser becomes immune to the infinite loop of left recursion. It allows the system to process the self-referencing rules that cause top-down models to stall. A bottom-up parser relies on two memory zones, a horizontal input buffer and a vertical stack. The first command, shift, moves a token into the stack. The second action, reduce, replaces matching stack symbols with a higher-level non-terminal, turning ID into T. Bottom-up parsing's complexity is built on these two decisions, moving data into memory with a shift or condensing it with a reduce. Let's watch this engine process a string. We begin by executing a shift operation, pulling our first token off the buffer and moving it into the stack. At this point, the engine looks for a handle, a specific substring on the stack that matches a grammar rule and can be safely reduced. Once it identifies a handle, it executes a reduction. This process, known as handle pruning, initiates the base of the parse tree structure. The loop continues. The stack doesn't contain a new handle yet, so the parser shifts the plus sign and then the final ID token onto the stack. Now we see a sequence of reductions. The top ID is pruned to a T, exposing the next handle. The engine condenses the entire sequence into the start symbol, completing the tree. This repeated identification and pruning of handles allows the parser to build a complete syntax tree from the raw leaves up to the root. But this engine has a vulnerability. To reach the start symbol, the parser must select the correct handle at every single step. A single wrong reduction leads to a dead end. This leads to a shift-reduced conflict. In this state, the symbols on the stack match a grammar rule, but shifting the next input token would also be valid. Without more information, the parser cannot determine which action leads to a successful parse. There is also the reduced-reduce conflict. This happens when the same stack contents match two different grammar rules simultaneously. The engine is stuck choosing between two different paths of condensation. Because the basic shift-reduce engine only looks at its current stack and the next token, it is frequently paralyzed by these points of ambiguity. We can resolve specific math-based ambiguities by using operator precedence parsing. This provides the engine with a set of hierarchy rules to force a decision. This precedence table tells the engine exactly when to delay a reduction. If the parser has a plus sign on the stack but sees a multiplication sign in the buffer, the table commands a shift, ensuring the higher priority operation is handled first. While these tables solve specific mathematical conflicts, they aren't enough to handle the complex grammars of modern programming languages, which require a more robust method of state management. The shift-reduce actions provide the mechanical movement, but to resolve every potential conflict, the engine needs the look-ahead tables and state logic found in LR parsers. That's where we'll go next.